For over 160 million years, dinosaurs have ruled an Earth of warmth and abundance. Vast forests stretch across continents, inland seas teem with strange marine life, and every corner of the planet hums with the sounds of a thriving age. On this last morning, life continues as if nothing has changed. A triceratops grazes in a fern-lined clearing, its slow movements framed by shafts of golden sunlight. From deeper in the forest comes the chorus of hadrosaurs carrying across the mist. Overhead, a giant pterosaur drifts silently toward the inland sea, its shadow gliding over the forest canopy. Then the southern sky blooms with a light more brilliant than the sun itself, an omen of a catastrophe so vast it will echo through deep time. Yet for the dinosaurs, the world still feels safe, for now. We are witnessing the final morning of the Cretaceous period, 66 million years ago. The world you're standing in is almost unrecognizably warm and lush. There are no ice caps anywhere on Earth. Global temperatures average about 15 degrees warmer than today. A massive inland sea splits North America down the middle, stretching from the Gulf of Mexico to the Arctic Ocean. This creates a tropical waterway where Colorado and Kansas now sit. The western interior seaway teems with life forms that would seem alien to our modern eyes. This is not a world in decline. Dinosaurs are at their absolute peak of diversity and abundance. They have ruled this planet for over 160 million years, with no sign of their dominance waning. Giant sauropods still browse the treetops. Fearsome tyrannosaurs patrol their territories. Herds of horned and duck-billed dinosaurs migrate across vast coastal plains. But hurtling toward this thriving world is a mountain of rock and ice, roughly 6 miles across. It travels at 12 miles every second. Born in the cold depths of space, this asteroid has wandered the outer solar system for millions of years. Now, gravitational forces send it careening toward our planet. Its destination, the shallow, sulfur-rich seas of what will one day be called the Yucatan Peninsula. Perhaps the worst possible place for it to strike. What follows is not the simple story of instant extinction that we often imagine. We're about to embark on a journey through one of the most complex catastrophes in Earth's history, a disaster that unfolded minute by minute, hour by hour, across days, months, and perhaps even centuries. In clearings throughout this forest, herds of hadrosaurs move with measured grace. Their complex vocal communications create an almost musical backdrop to the morning as different species call and respond across the landscape. Some wade into shallow lagoons to feed on aquatic plants. Others use their distinctive crests as resonating chambers, sending low-frequency calls that travel for miles through the dense forest. Moving through this herbivorous paradise are the predators that have made the Cretaceous famous. A Tyrannosaurus rex stalking through morning shadows is a marvel of evolutionary engineering. 7 tons of muscle and bone moving with surprising grace. Its massive skull houses a brain capable of complex problem-solving. Its eyes provide binocular vision that would make any modern predator envious. High above the forest canopy, pterosaurs rule the skies with mastery that won't be seen again until the evolution of modern birds. Some are as small as sparrows, flitting between flowers in search of nectar and insects. Others, like the magnificent Quetzalcoatlus, are true giants with wingspans rivaling small aircraft. In what will one day be North Dakota, a particular river valley bustles with life that will make this location famous to paleontologists millions of years in the future. Fish swim in clear, meandering streams, sturgeons and paddlefish whose ancient lineages stretch back hundreds of millions of years. Turtles bask on fallen logs, while insects create their own complex aerial ballets above the water's surface. This is the place that will become known as Tanis. What makes this morning particularly poignant is the absolute normalcy of it all. This is a world that has been stable for millions of years. Evolutionary processes have had time to craft intricate relationships between predator and prey, plant and pollinator, land and sea. It's this very richness that makes what's about to happen so devastating. This is not a world in crisis. This is life at its most exuberant and diverse, blissfully unaware that in just a few hours, everything will change forever. To understand what's about to strike Earth, we must journey backward through time and space. Millions of years ago, in the cold depths beyond Jupiter's orbit, gravitational forces shaped debris left over from our solar system's formation. One particular chunk of rock and ice was destined for a more dramatic fate. This was no ordinary asteroid, composed primarily of carbonaceous chondrite, a primitive mixture of rock, ice, and organic compounds. It contained the elements that would prove most catastrophic for Earth. Rich in sulfur, carbon, and water, it was like a massive chemical bomb wrapped in stone. Had it been composed of ordinary rock, the coming catastrophe might have been survivable. For millions of years, this mountain-sized harbinger of doom followed a stable orbit in the outer reaches of our solar system, just one of countless similar objects in the cold darkness between worlds. It was ancient when the first dinosaurs appeared on Earth, already old when life itself was still experimenting with complex forms. But gravitational forces in space are subtle and patient. Over millions of years, the combined influences of Jupiter and the other giant planets began to nudge this asteroid's orbit. Like a marble rolling down a cosmic hill, once the process began, there was no stopping it. As our asteroid crossed Earth's orbit and began its final descent, this cosmic projectile was traveling at 20 kilometers per second, or about 45,000 miles per hour. To put this in perspective, a bullet travels at roughly 1,000 miles per hour. This asteroid was moving 45 times faster than that, carrying kinetic energy equivalent to 100 million atomic bombs. The asteroid's trajectory brought it in at approximately a 60-degree angle to Earth's surface, steep enough to maximize the transfer of energy, shallow enough to ensure it wouldn't simply punch through the atmosphere and exit on the other side. It was, in engineering terms, the perfect angle for maximum destruction. In its final moments, as it screamed through Earth's atmosphere, the asteroid experienced forces that would have pulverized ordinary rock. The air in front of it compressed to temperatures exceeding those found in the sun's corona, creating a plasma sheath that turned night to day across half the continent. The last few seconds of its journey were almost anticlimactic in their brevity. From the moment it entered Earth's atmosphere to the moment of impact took less than 10 seconds. Any animals witnessing its approach would have seen a brilliant fireball streaking across the sky, growing brighter and larger until it outshone the sun itself. And then, at exactly 10:30 a.m. local time on what would have been a beautiful spring morning, this visitor from the depths of space completed its multi-million-year journey. It struck the shallow seas off the Yucatan Peninsula with more force than the Earth had experienced in 65 million years. At precisely 10:30 a.m. local time, the 6-mile-wide asteroid completed its cosmic journey. In that instant, more energy was released than in any event since Earth's formation, an explosion equivalent to 100 million times the power of the largest nuclear weapon ever detonated. The moment of contact lasted mere microseconds. In that brief span, physics operated at its most extreme. The asteroid's front edge struck the seafloor while its rear was still miles above the surface, creating pressures that exceeded anything found naturally on Earth. The rock beneath the impact point didn't simply break, it behaved like a liquid, flowing and splashing upward in ways that solid stone was never meant to move. Temperatures at the point of contact reached 10,000 degrees Celsius, hot enough to vaporize any known material instantly. The seafloor became a temporary window into the planet's interior as the asteroid punched through sedimentary layers, through bedrock, and deep into the crystalline basement rocks. In seconds, a hole was excavated that was 20 miles deep, deep enough to swallow Mount Everest, with room to spare. The asteroid didn't simply disappear into this crater. Most of it was instantly vaporized by the incredible pressures and temperatures, creating a fireball of superheated rock and gas that expanded outward at velocities approaching 30,000 miles per hour. This expanding plasma cloud contained the vaporized remains of both the asteroid and millions of tons of Earth's crust, all heated to temperatures that transformed solid matter into something resembling the interior of a star. The shockwave that radiated outward moved faster than the speed of sound, compressing the air in front of it to create a pressure wave that would be felt around the world. This wasn't simply an earthquake. It was the most powerful seismic event in Earth's geological history, generating forces equivalent to a magnitude 10 earthquake. To put this in perspective, the most powerful earthquake ever recorded by modern instruments was magnitude 9.5. This impact generated shockwaves at least 10 times more powerful. As the initial fireball expanded, it began to launch material into space at velocities exceeding Earth's escape velocity. Millions of tons of molten rock were blasted upward at speeds of several miles per second. Some reached altitudes of over 60 miles before beginning their deadly return journey. This ejecta would cool and solidify during its brief journey through space, forming billions of glass spherules that would soon rain down across the entire planet. The crater itself was growing with each passing second, not through continued excavation, but through the collapse and flow of superheated rock. Mountains the height of the Himalayas rose and fell within minutes as the Earth's crust struggled to accommodate the massive disruption. But perhaps most significantly, for the future of life on Earth, the impact occurred in exactly the wrong place. The Yucatan Peninsula's bedrock contains massive deposits of sulfur-rich minerals. The asteroid's impact vaporized these deposits, launching enormous quantities of sulfur into the atmosphere where it would combine with water vapor to form sulfuric acid aerosols. Had the asteroid struck almost anywhere else on Earth, the long-term climatic effects might have been far less severe. As the first few minutes passed, the initial chaos began to organize itself into patterns that would define the coming catastrophe. The expanding fireball reached its maximum size and began to cool, while the debris launched into space began its deadly return journey to Earth. Seismic waves were racing through the planet's crust at thousands of miles per hour, triggering earthquakes and volcanic eruptions thousands of miles from the impact site. In those first critical minutes, as debris began to rain down and shock waves raced across continents, the Cretaceous world was still largely intact. Dinosaurs still grazed in distant meadows, fish still swam in clear streams, pterosaurs still soared through skies that had not yet begun to darken. The impact had occurred, but its full effects were only beginning to unfold. 15 minutes after the initial impact, the first consequences of the catastrophe began to reach the Tanis River Valley in what is now North Dakota, some 2,000 miles from the impact site. To the creatures living there, the morning had begun like any other, fish swimming lazily in clear streams, turtles basking on fallen logs, small mammals beginning their daily foraging, but the laws of physics were already carrying death toward them at incomprehensible speeds. The seismic waves arrived first, racing through Earth's crust at nearly 4 miles per second. When they reached the Tanis region, the ground began to shake with a violence unlike anything these animals had ever experienced. Trees swayed gently at first, then more violently. Birds lifted from their perches in confusion. The normally placid streams and ponds began to slosh back and forth. High above, something extraordinary was happening to the sky itself. The first of the impact debris, millions of tiny glass spherules formed from rock that had been blasted into space, were beginning their deadly descent through the atmosphere. These tektites, ranging in size from microscopic dust to spheres nearly an inch across, were re-entering Earth's atmosphere at velocities of several miles per second. As these glass spherules encountered the atmosphere, friction heated them to glowing temperatures. The sky became a display of deadly beauty. To any observer witnessing it, the heavens would have appeared to be raining fire, countless points of light streaking downward like a gentle aurora that promised wonder rather than death. The thermal radiation from billions of re-entering spherules began to warm the atmosphere itself, raising temperatures across entire continents by several degrees within minutes. In the Tanis Valley, the first spherules began falling like supernatural snow. Initially, there were just a few scattered droplets, mysterious glass beads that intrigued the local wildlife. Fish rose to the surface to investigate these strange objects. Insects and small animals touched them with curiosity rather than fear. But within minutes, what had begun as a gentle shower became a steady downpour of molten glass. The fish were among the first to understand that something was wrong. As more and more spherules fell into the water, they began to clog the gills of filter-feeding species like sturgeon and paddlefish. These ancient fish, whose lineages stretched back hundreds of millions of years, had survived countless environmental changes, but they had no preparation for breathing glass. Distress spread through the aquatic community as fish moved restlessly at the surface, trying to clear their respiratory systems of the foreign particles. Meanwhile, the continued seismic activity was creating something that would prove crucial to preserving this moment for science. The violent shaking triggered what geologists call siege waves, standing waves in confined bodies of water that can be generated by seismic activity. Think of what happens when you gently rock a bathtub full of water, causing the liquid to slosh back and forth. The same process was occurring in the rivers and ponds around Tanis, but with consequences for anything living in or near the water. These seiche waves, some reaching heights of 10 to 20 feet, began surging back and forth across the landscape with rhythmic regularity. Each wave carried with it sediment, vegetation, and increasingly, the bodies of animals that had succumbed to the glass rain or been caught in the oscillating waters. Tree trunks, some still warm from the thermal pulse, were swept along with the moving waters, creating a mixture of organic and inorganic debris. The spherules themselves told a story of the impact's incredible violence. Some were perfectly spherical, having cooled slowly during their journey through space. Others were elongated or flattened, showing evidence of having collided with other particles during their formation. Chemical analysis would later reveal that they contained elements from both the asteroid and Earth's crust, mixed at the atomic level, a signature that could only have been created by the extreme temperatures and pressures of the impact event. As the glass rain intensified, reaching its peak about 45 minutes after impact, the very air became difficult to breathe. The thermal radiation from the re-entering debris was warming the atmosphere to temperatures that would have been uncomfortable for many terrestrial animals. Small mammals and reptiles sought shelter wherever they could find it, under logs, in burrows, beneath rock overhangs. But for many, there was simply nowhere to hide from the planet-wide thermal pulse. The forest canopy provided some protection, but at a cost. Leaves and branches began to wilt from the intense heat, while some trees began to smolder as the thermal radiation approached their ignition point. The air filled with gentle wisps of smoke, adding to the atmospheric haze and creating an otherworldly atmosphere. Perhaps most remarkably, some of the spherules fell into tree resin that was seeping from damaged conifers. This resin, which would eventually fossilize into amber, captured the glass beads in perfect preservation, creating time capsules that would allow scientists 66 million years later to study the exact composition and structure of the impact debris. By the end of the first hour, the Tanis ecosystem was already transformed. The clear streams had become clouded torrents filled with debris and struggling fish. The forest floor was carpeted with glass spherules, scattered animal bodies, and gently smoldering vegetation. The air itself shimmered with heat and was thick with particles that made breathing a challenge for any surviving animals. Yet remarkably, this was still just the beginning. The spherular bombardment, transformative as it was, represented only the fastest moving component of the impact debris. Larger chunks of rock, some the size of boulders, were still following ballistic trajectories that would bring them back to Earth over the coming hours. The seismic waves would continue to circle the globe multiple times, triggering earthquakes and volcanic eruptions on the far side of the planet. Most ominously, the massive quantities of sulfur and dust blasted into the stratosphere were beginning to spread around the globe, carried by high-altitude winds that would distribute the impact's effects to every corner of the Earth. The stage was set for a global catastrophe that would unfold over days, weeks, and months. As the second hour dawned after impact, the Earth itself had become something transformed. The seismic waves generated by the asteroid strike were racing around the planet at thousands of miles per hour. When these waves encountered fault lines, dormant volcanoes, and unstable geological formations, they triggered secondary disasters that multiplied the destruction far beyond what the impact itself had caused. In the Deccan Traps of what is now India, massive volcanic systems that had been quietly building pressure for millennia suddenly stirred to life. The seismic trigger of the impact provided the final push needed to unleash flows of lava that would travel for thousands of miles, adding their own contribution of ash, sulfur dioxide, and carbon dioxide to an atmosphere already thick with impact debris. But it was in the ocean basins that some of the most spectacular secondary effects were unfolding. The initial impact had displaced an enormous volume of water from the Gulf of Mexico, creating tsunami waves that were now racing across ocean basins at the speed of jet aircraft. These weren't ordinary tsunamis. These were walls of water hundreds of feet high, carrying the energy of the most powerful explosion in Earth's recent history. When these mega tsunamis encountered the shallow waters of continental shelves, they began to build to truly extraordinary heights. Along the Gulf Coast, waves over 300 feet tall swept inland for hundreds of miles, carrying with them a cargo of molten debris, shattered rock, and superheated steam. Entire ecosystems were gently lifted from the landscape and deposited in mixed assemblages dozens of miles inland. Meanwhile, back at the Tanis site, the Seiche waves had reached a steady rhythm. Every 20 to 30 minutes, massive surges of water swept across the river valley, each one carrying more sediment, debris, and organic matter than the last. The fish that had initially succumbed to the glass rain were now being joined by larger animals, turtles, crocodilians, and early mammals that had been caught in the oscillating floods. The preservation conditions being created by these waves were extraordinary and unique in the geological record. Each surge deposited a distinct layer of sediment, creating a timeline that could be read like pages in a book. Fish were buried in three-dimensional positions, their bodies filling with sediment before decay could set in. Perhaps most remarkably, the waves were also preserving evidence of the exact timing of death. Fish would later be found with tektites still lodged in their gills, direct evidence that they had been breathing glass spherules when the final surge buried them. The thermal effects of the impact were now becoming globally apparent. The re-entering debris had warmed the atmosphere to temperatures that ignited forests across entire continents. In North America, wildfires began appearing from the thermal pulse, creating displays of light that stretched from Mexico to the Arctic Circle. These weren't ordinary forest fires. They were displays of unprecedented scale, generating their own weather systems and creating winds that spread the flames in graceful patterns across the landscape. The smoke from these continental fires began to merge with the dust and sulfur already filling the atmosphere. Visibility dropped to short distances in many areas as the air became thick with particulates. The sun, when visible at all, appeared as a dim red disk struggling to penetrate the growing atmospheric haze. Temperatures began to fluctuate, warming from the thermal pulse, followed by gradual cooling as the sun's rays were increasingly filtered by airborne debris. Animal behavior during these hours reveals the remarkable adaptability that life displays in crisis. Herding animals that had maintained complex social structures for millions of years began seeking shelter together in new ways. Predators paused their hunting to focus on finding protection from the rain of fire and glass. Many species displayed behaviors never before seen, creative adaptations to a world that had suddenly become unfamiliar. The atmospheric chemistry was changing by the hour as well. The vaporized sulfur from the impact site was combining with water vapor to form sulfuric acid droplets that began falling as acidic rain. This precipitation was strong enough to damage exposed vegetation and alter the chemistry of standing water. The very air was becoming laden with particles of glass, ash, and chemical compounds that no terrestrial life form had ever encountered. Ocean ecosystems, previously buffered from the worst effects by the thermal mass of water, were now beginning to experience their own transformation. The impact had triggered massive underwater landslides along continental margins, burying seafloor communities under layers of sediment. The acidic rain was beginning to change the chemistry of surface waters, making them challenging for the plankton that formed the base of marine food webs. The largest debris from the impact was now beginning to return to Earth, having followed ballistic trajectories that carried them thousands of miles from the impact site. These boulder-sized chunks of molten rock created secondary craters when they struck, each one generating its own local shockwave and adding to the growing transformation. By the 6th hour after impact, the global nature of the change was becoming undeniable. The atmospheric disruption had created weather patterns unlike any in recent experience. Strong winds carrying debris at ground level, electrical storms that lasted for hours, and temperature swings that challenged large animals' ability to regulate their body heat. The very air had become thick with particles that challenged respiratory systems and carried compounds that were foreign to any creature adapted to breathe them. Yet even amid this unprecedented transformation, life was displaying the resilience that had carried it through previous challenges. Small animals that could burrow underground found themselves with crucial advantages. Aquatic animals in deep lakes and rivers were somewhat protected from the thermal pulse and acidic rain. Some plants, their leaves damaged, were already beginning to send up new growth from underground root systems. The stage was now set for the long-term effects that would define the extinction event. The immediate drama of the impact was giving way to more subtle but equally significant changes in global climate and atmospheric chemistry. 24 hours after the asteroid impact, Earth had been transformed into a planet that would have been unrecognizable to any creature that had known it just one day earlier. The The immediate drama of the first few hours had given way to something more profound, the systematic alteration of environmental systems that had supported life for hundreds of millions of years. The atmosphere itself had become a filtering shroud of dust, ash, and chemical aerosols that blocked most of the sun's radiation. What had been a brilliantly clear spring morning was now a twilight world where noon looked like dusk and dusk became indistinguishable from night. The fine particles suspended in the air created an unusual red glow that bathed everything in otherworldly light. Across North America, the continental wildfires that had begun with the thermal pulse were now burning steadily, consuming forests that had stood for thousands of years. These fires generated their own weather systems, creating spiraling columns of smoke and ash that could reach heights of several miles. The smoke from these fires merged with the impact debris to create an atmospheric mixture of unprecedented complexity. The temperature fluctuations were becoming more extreme and unpredictable. Areas that had experienced the full force of the thermal pulse were still radiating heat like enormous furnaces, while regions shielded by clouds or geography were already beginning to cool as the sun's energy was increasingly blocked by atmospheric particles. This created pressure differentials that spawned storms of remarkable violence, hurricanes that formed over land, tornadoes that lasted for hours, and wind patterns that could level entire stands of trees. In the Tanis River Valley, the Seiche waves had finally begun to subside, but not before depositing over 6 feet of sediment across the entire ecosystem. The final layers of this deposit contained an extraordinary record of the catastrophe, a mixture of local and far-traveled materials that included pieces of trees from hundreds of miles away, marine organisms from the western interior seaway, and even fragments of the impact crater itself. The chemical composition of the atmosphere was changing rapidly as the vaporized sulfur from the impact site combined with water vapor to create quantities of sulfuric acid aerosols. These microscopic droplets were beginning to condense around particles of dust and ash, creating an increasingly dense haze that not only blocked sunlight but also began to fall as acidic rain. This wasn't ordinary acid rain. This was precipitation with the power to damage bark on trees and affect the exposed skin of any animal caught in the open. The ocean systems were experiencing their own cascade of changes. The massive tsunamis had not only altered coastal ecosystems, but had also disrupted the delicate layering of ocean waters that maintained global circulation patterns. Cold, nutrient-rich water from the depths was no longer rising to the surface as efficiently, while warm surface water was being prevented from sinking. More immediately significant for marine ecosystems was the rapid acidification of surface waters. The sulfuric acid falling from the atmosphere was lowering the pH of seawater to levels that began to dissolve the shells of microscopic plankton, the foundation of all marine food webs. Foraminifera, tiny shelled creatures that had thrived in Earth's oceans for hundreds of millions of years, were literally dissolving in water that had become increasingly acidic. The soil itself was being altered by the mixture of metals and compounds falling from the sky. The asteroid had been rich in elements like iridium, osmium, and platinum, normally rare on Earth's surface but common in extraterrestrial objects. These metals, along with other compounds created by the extreme temperatures and pressures of impact, were settling into the soil and groundwater, creating contamination that would persist for decades. Plant communities were facing multiple challenges that threatened their existence. The initial thermal pulse had damaged exposed vegetation across entire continents. The acidic rain was now affecting what foliage remained, while the blocked sunlight was making photosynthesis increasingly difficult. Most critically, the soil contamination was interfering with root systems, preventing even hardy plants from absorbing the nutrients they needed to survive. The impact on insect populations was particularly severe and would have cascading effects throughout terrestrial ecosystems. Flying insects were especially vulnerable to the particle-laden atmosphere, with many species experiencing respiratory difficulties as their tiny airways became clogged with dust and ash. The loss of these crucial pollinators meant that even plants that survived the initial assault would struggle to reproduce, setting the stage for widespread plant difficulties in the months to come. Animal behavior had become increasingly adaptive and flexible. Many species that had never interacted before were now finding themselves together in the few remaining refugia, caves, deep burrows, and other sheltered locations. Traditional territorial boundaries and social hierarchies were giving way as survival became the primary focus. Herbivores that could no longer find their preferred plants began scavenging on other organic matter, while some species developed new feeding strategies in their effort to adapt. The water cycle itself was being disrupted by the massive amounts of particles in the air, which served as condensation nuclei for cloud formation. In some areas, this created intense downpours of acidic rain that damaged the landscape, while other regions experienced drought as the disrupted atmospheric circulation failed to deliver moisture. Perhaps most significantly, the first signs of global cooling were beginning to appear. While the immediate effects of the thermal pulse had raised temperatures dramatically, the increasing atmospheric opacity was now blocking more and more solar radiation from reaching Earth's surface. Temperature measurements, if they had been possible, would have shown the beginning of a decline that would continue for months. The sounds of the changing planet were unlike anything in Earth's history. The normal sounds of a living world, bird songs, insect buzzing, the rustle of leaves in the wind, had been replaced by a different symphony of wind moving through altered forests, the distant rumble of ongoing earthquakes, and the unusual quiet of ecosystems that had fallen still. Wildlife refugia that had provided safety during previous environmental changes were now proving inadequate against the scope of this transformation. Mountain valleys that had sheltered species during ice ages were filled with acidic ash. Deep caves that had provided refuge during volcanic eruptions were now chambers where animals slowly adapted to contaminated air. Even the deep ocean, traditionally the most stable environment on the planet, was becoming increasingly challenging to life. The breakdown of ecological relationships was perhaps the most profound aspect of this global transformation. Partnerships that had evolved over millions of years were dissolving as partner species died or relocated. Networks of connections that linked plants across vast distances were collapsing as both pollinators and flowering plants succumbed to the altered environment. Predator-prey relationships that had maintained ecosystem balance for geological ages were vanishing as both hunters and hunted faced new challenges. Yet even in this transformed hour, the seeds of recovery were being planted. Some plant species had evolved underground storage organs that could survive even complete destruction of their above-ground parts. Bacterial and fungal communities in the soil, while stressed by the contamination, retained the genetic diversity that would eventually allow ecosystems to rebuild. Most importantly, some animals, particularly small, adaptable species with low metabolic requirements, were finding ways to survive in this transformed world. As the first day ended and an unusual night descended over the planet, Earth had completed its transformation from a vibrant, life-supporting world to something resembling an alien landscape. But this was still just the beginning of the extinction event. The immediate drama of the impact had given way to more subtle but equally significant long-term effects that would continue to unfold over the coming weeks, months, and years. The real test of life's resilience was yet to come. In the days following the impact, as the immediate chaos began to settle into a new routine, Earth entered what scientists would later term impact winter, a period of prolonged darkness and cold that would test the limits of life's adaptability. The sun, when visible at all through the atmosphere, appeared as a pale red disk struggling to penetrate the global shroud of dust, ash, and sulfuric acid aerosols. By the end of the first week, global temperatures had dropped by an average of 15 to 20 degrees Fahrenheit. Some regions experienced even more dramatic cooling. This wasn't the gradual temperature change that species had adapted to during ice ages. This was a steep decline that occurred over days rather than millennia. Animals that had evolved in the warm, stable climate of the late Cretaceous suddenly found themselves struggling to maintain their body temperature in conditions more severe than any recent ice age. The atmospheric opacity was now blocking an estimated 90 to 99% of normal sunlight from reaching Earth's surface. This near-total darkness had catastrophic implications for photosynthesis, the fundamental process that had supported virtually all life on Earth for over 1 billion years. Across the globe, plants began to shut down their photosynthetic machinery, first slowing their growth, then entering dormancy, and finally beginning to die as their stored energy reserves were exhausted. The collapse of plant communities triggered a domino effect that reverberated through every terrestrial ecosystem. Herbivorous dinosaurs, which had thrived on abundant vegetation for over 160 million years, faced starvation on a scale that defied imagination. The massive sauropods, some weighing over 100 tons, required enormous quantities of plant matter to fuel their metabolism, quantities that were simply no longer available anywhere on the planet. Large herbivores like Triceratops and Edmontosaurus, which had dominated Cretaceous landscapes in vast herds, began dying in significant numbers within the first few weeks. Their social structures, which had evolved over millions of years to coordinate migration and defense, became meaningless in a world where there was simply nowhere to migrate to find food. The carnivorous dinosaurs initially seemed to have an advantage, as the die-offs provided abundant carrion for scavenging. Tyrannosaurus rex and other large predators temporarily benefited from this windfall, but it was a temporary prosperity that couldn't last. As the supply of fresh carcasses dwindled and decomposition slowed in the cooling environment, even the apex predators began to face starvation. Smaller theropods demonstrated remarkable behavioral flexibility during this period, switching from their normal prey to insects, small mammals, and even plant material when available. Some species may have developed cooperative scavenging behaviors, working together to process carcasses more efficiently than individual hunters could manage. But even these adaptations could only delay the inevitable in an ecosystem where the fundamental energy source, sunlight, had been largely eliminated. The marine environment was experiencing its own catastrophic collapse, though the effects unfolded somewhat differently than on land. The ocean's thermal mass provided some protection from the immediate temperature changes, but the acidification of surface waters was proving lethal to countless species. Ammonites, which had survived every previous extinction event for over 400 million years, began disappearing from the fossil record as their shells dissolved in increasingly acidic seawater. Plankton communities, the microscopic foundation of all marine food webs, were devastated by the combination of acidic rain, reduced sunlight, and temperature changes. The death of these tiny organisms created a cascade effect that rippled through the entire ocean ecosystem. Fish populations crashed as their food sources disappeared, which in turn led to the starvation of marine reptiles like mosasaurs and plesiosaurs. The atmospheric chemistry continued to evolve in ways that made survival increasingly difficult for any remaining life. The sulfur dioxide released by the impact was combining with water vapor to create sulfuric acid aerosols that not only blocked sunlight, but also created acidic rain with a pH comparable to vinegar. This corrosive precipitation was stripping the bark from trees, poisoning water sources, and making the very air challenging to breathe. Insect populations, already stressed by the initial thermal pulse and debris fall, were now facing widespread collapse. These creatures, which had shown remarkable resilience through previous extinction events, were particularly vulnerable to the combination of temperature changes and atmospheric contamination. The loss of insects had immediate implications for the few plant species still attempting to reproduce, as most flowering plants depended on insect pollination. Animal behavior during this period reveals the desperate measures that species took to survive. Many animals entered a form of induced hibernation, slowing their metabolism to conserve energy. Others abandoned their normal territories entirely, migrating vast distances in search of any area where conditions might be slightly more tolerable. Some species that had never interacted before formed temporary alliances, sharing body heat and food resources in caves and other sheltered locations. The soil ecosystem was undergoing its own transformation as the surface environment became increasingly hostile. Earthworms and other soil organisms either died or burrowed deeper underground, disrupting the processes that had maintained soil health for millions of years. The lack of leaf litter and other organic matter meant that decomposition cycles were breaking down, leading to the accumulation of unprocessed organic matter in some areas and complete depletion in others. Water sources were becoming increasingly scarce and contaminated. The acidic rain was poisoning surface water, while the disrupted weather patterns were creating severe droughts in many regions. Animals that survived the initial catastrophe often succumbed to dehydration or poisoning from contaminated water sources. Even groundwater was becoming polluted as toxic compounds from the impact debris leached through the soil. As the weeks passed, the silence of extinction began to replace the sounds of a living planet. The dawn chorus of birds fell quiet as avian species succumbed to starvation and respiratory distress. The calls of large dinosaurs, which had echoed across Cretaceous landscapes for millions of years, became increasingly rare and eventually stopped altogether in many regions. Even the buzz of insects, the background soundtrack of terrestrial life for hundreds of millions of years, faded to near silence. Yet even in this global catastrophe, patterns of survival and extinction were beginning to emerge. Animals with certain characteristics, small size, low metabolic rates, flexible diets, and the ability to enter dormancy, were proving more resilient than others. Burrowing species had distinct advantages over surface dwellers, while aquatic animals in deep, large bodies of water were somewhat buffered from the worst atmospheric effects. As the immediate aftermath of the impact gave way to the grinding reality of long-term environmental collapse, Earth entered a phase that paleontologists refer to as the Long Death, a period of sustained ecosystem breakdown that would stretch across months and gradually winnow the survivors down to only the most adaptable and resilient species. By the end of the first month, the global temperature had stabilized at its new, lower level. But this stability was itself a kind of death sentence. The impact winter was no longer a temporary shock to the system. It had become the new normal, with atmospheric conditions showing no signs of improving. The sun remained a pale ghost of its former self, struggling to penetrate an atmospheric shroud that seemed to thicken rather than clear. The plant kingdom, the foundation of all terrestrial ecosystems, was now in full collapse. The lucky few plants that had managed to survive the initial weeks were exhausting their stored energy reserves and beginning to die. Forests that had stood for thousands of years were reduced to graveyards of standing dead trees, their bark stripped away by acidic rain, their branches bare of leaves that would never return. Large herbivorous dinosaurs, the ecological engineers that had shaped Cretaceous landscapes for over 100 million years, were disappearing at an accelerating rate. The massive sauropods were among the first to vanish completely. Their enormous size, which had been such an advantage during millions of years of abundance, now became a fatal liability. A brontosaurus, or Argentinosaurus, required hundreds of pounds of vegetation daily to survive, but such quantities were no longer available anywhere on the planet. The horned dinosaurs, Triceratops, Centrosaurus, and their relatives, lasted somewhat longer due to their ability to process lower quality plant material, but they too began to succumb as even the toughest vegetation became scarce. Their sophisticated social behaviors, which had allowed them to migrate seasonally and defend against predators, became meaningless in a world where there was nowhere to migrate to. Duck-billed dinosaurs like Edmontosaurus and Parasaurolophus, with their efficient teeth for processing tough plant material, represented some of the last holdouts among large herbivores. But even their specialized digestive systems couldn't extract nutrition from dead vegetation. Their elaborate vocal communications fell silent as their populations dwindled to scattered dying remnants in isolated refugia. The carnivorous dinosaurs faced their own unique form of extinction. Initially, the massive die-offs had provided abundant carrion, but as the supply of fresh carcasses dwindled, competition became fierce. Tyrannosaurus rex, the apex predator of its era, was reduced to scavenging alongside much smaller animals, fighting over scraps in scenes that would have been unimaginable just months before. Smaller theropods showed remarkable behavioral flexibility, switching to insects, eggs, and even plant material when meat became unavailable. Some species may have formed temporary social bonds, sharing food resources and body heat in ways their ancestors never did. But even these adaptations could only delay the inevitable. Without a functioning ecosystem to support them, even the most adaptable predators were ultimately doomed. The marine environment was experiencing its own prolonged collapse. The ocean's thermal mass had buffered marine life from the immediate temperature changes, but the ongoing acidification was proving lethal on a scale that defied comprehension. Surface waters had become so acidic that they were literally dissolving the shells and skeletons of countless marine organisms. Ammonites, those graceful, spiral-shelled creatures that had dominated marine environments for hundreds of millions of years, were vanishing from the fossil record with heartbreaking finality. Their shells, once preserved in abundance, became increasingly rare as the increasingly acidic ocean dissolved them even after death. The collapse of plankton communities was creating a crisis that reverberated through every level of marine food webs. These microscopic organisms were dying in such vast numbers that their dead cells were raining down through the water column like organic snow. This massive influx of decaying matter was consuming oxygen as it decomposed, creating dead zones that expanded week by week. Marine reptiles like mosasaurs and plesiosaurs, the ocean's apex predators, were facing starvation as their prey disappeared. These magnificent creatures, some over 50 feet long, were reduced to scavenging on the ocean floor, competing with bottom-dwelling scavengers for any organic matter they could find. Terrestrial vertebrates were displaying increasingly desperate survival strategies as the months wore on. Some species that had never before shown hoarding behavior began caching any food they could find. Others began altering their reproductive strategies, with some species attempting to breed earlier or more frequently in a desperate attempt to ensure their genetic legacy before extinction. The few remaining plant species were showing signs of evolutionary stress that would have implications lasting millions of years. Many were investing their remaining energy in seed production rather than growth, creating massive seed banks that would remain dormant in the soil for decades or centuries. By the 6th month after impact, the transformation was complete. Earth had become a planet where silence was the norm and life the exception. The great dinosaur dynasties that had ruled for over 160 million years were either extinct or reduced to tiny, scattered populations clinging to existence in isolated refugia. Yet even in this darkest period, the seeds of recovery were present. Some bacterial and fungal communities had not only survived, but were beginning to adapt to the new chemical environment. A few plant species were maintaining dormant underground root systems. Most importantly, some small animals, particularly those with low metabolic rates and flexible diets, were finding ways to survive in ecological niches that the large dinosaurs could never exploit. The age of dinosaurs was ending, but the age of mammals was about to begin. 6 months after the asteroid impact, Earth had become a planet divided between the dying and the surviving. The boundary between these two groups was often determined by factors as simple as body size, metabolic rate, or the ability to burrow underground. The great sorting had begun, evolution's judgment on which forms of life possessed the characteristics necessary to survive in a world transformed beyond recognition. Size, it turned out, was destiny. Animals weighing more than 55 pounds faced extinction rates approaching 100%, while smaller creatures had dramatically better odds of survival. This wasn't simply a matter of food requirements, it was a fundamental rule of physics and physiology that governed how animals responded to environmental stress. Large animals, with their high metabolic rates and substantial food requirements, were like vehicles trying to navigate an energy crisis. A Tyrannosaurus rex needed to consume hundreds of pounds of meat per week to maintain its massive frame. But in a world where large prey animals were extinct and carrion was increasingly scarce, such requirements became impossible to meet. Small mammals, by contrast, were perfectly positioned for survival. Species like the early marsupial alphodon and primitive placental mammals required only a few ounces of food per day, requirements that could be met by scavenging insects, seeds, and small amounts of organic matter. Their fur provided insulation against the cooling climate, while their small size allowed them to shelter in burrows, hollow logs, and rock crevices. The metabolic advantages of small size extended beyond simple food requirements. Small animals could enter torpor or hibernation-like states when food became scarce, essentially shutting down their metabolism to survive on stored fat reserves. Large dinosaurs, with their higher baseline metabolic rates, lacked this flexibility and were forced to continue burning energy even when food was unavailable. Dietary flexibility emerged as another crucial survival trait. Animals that had evolved as specialists found themselves at a severe disadvantage when their preferred food sources disappeared. Generalists and opportunistic feeders, by contrast, could switch between different food sources as availability changed. The early mammals exemplified this dietary flexibility. While some modern mammals are highly specialized feeders, their Cretaceous ancestors were largely omnivorous, capable of eating insects, seeds, fruits, small vertebrates, and even carrion when available. Birds, the surviving lineage of dinosaurs, demonstrated many of the same survival characteristics that benefited mammals. Their small size, ability to fly to new food sources, and often omnivorous diets gave them crucial advantages. Some early bird species could enter torpor, while others were already adapted for seasonal migration. the burrowing lifestyle provided perhaps the most significant survival advantage of all. Animals that lived underground were protected from the temperature extremes, acidic rain, and atmospheric toxins that were lethal to surface-dwelling creatures. Burrows also provided stable microclimates, where temperatures remained more constant and humidity levels were higher than on the devastated surface. Small mammals like multituberculates, early relatives of modern rodents, were already highly adapted for underground life. Their powerful digging claws and streamlined body shapes allowed them to excavate extensive burrow systems that could shelter entire family groups. Amphibians demonstrated another survival strategy that proved effective in the post-impact world. Their permeable skin actually allowed them to absorb oxygen directly from water and moist soil, reducing their dependence on atmospheric air that had become toxic with particulates and acid vapors. Many amphibian species could also enter extended periods of dormancy. Freshwater turtles and crocodilians represented success stories among larger vertebrates. These reptiles possess several crucial advantages: semi-aquatic lifestyles that protected them from atmospheric toxins, ectothermic metabolism that reduced their food requirements, and the ability to enter dormancy during harsh conditions. Aquatic environments, particularly large, deep bodies of water, provided some buffering against the worst effects of the impact winter. The thermal mass of water moderated temperature changes, while depth provided protection from acidic rain and atmospheric contamination. The plant kingdom's survival strategy was fundamentally different from that of animals. Rather than maintaining active individuals through the crisis, many plant species survived as dormant structures, seeds, spores, bulbs, and underground root systems that could wait out the environmental catastrophe. Some plant species had evolved specific adaptations for surviving fire, drought, and other environmental stresses that proved useful during the impact winter. Plants with deep root systems could access groundwater when surface water became toxic. Species with waxy or hairy leaves were better protected against acidic rain. Bacterial and fungal communities were perhaps the most successful survivors of all. These microorganisms possessed genetic flexibility that allowed rapid adaptation to new environmental conditions. Some bacteria could actually thrive on the toxic compounds released by the impact, while certain fungi could decompose organic matter under conditions that would have been impossible for other decomposers. The role of geographic location in determining survival cannot be overstated. Certain regions, particularly those at higher latitudes, areas with deep cave systems, and locations near large bodies of water, provided refugia where survival was more likely. Perhaps most importantly, chance played an enormous role in determining which individuals and populations survived. Animals that happened to be in burrows when the thermal pulse struck, plants whose seeds were buried deep in soil, marine organisms living in areas with slightly less acidic water. These random factors often made the difference between extinction and survival. The genetic consequences of this massive filtering event were profound. Surviving populations were often reduced to tiny numbers, creating genetic bottlenecks that would influence evolution for millions of years to come. As the sixth month after impact drew to a close, the pattern was clear. Earth's biosphere had been fundamentally restructured. The age of giant reptiles was ending, not with a sudden catastrophe, but with a gradual winnowing that favored small, adaptable, behaviorally flexible organisms. As scientists have delved deeper into the fossil record, using increasingly sophisticated techniques, a surprising and controversial picture has emerged of dinosaur survival after the asteroid impact. While the traditional narrative suggests that all non-avian dinosaurs perished within months of the catastrophe, new evidence from sites in New Mexico and Colorado hints at a more complex story. The most compelling evidence comes from the Ojo Alamo Formation in the San Juan Basin of New Mexico, where paleontologists have discovered dinosaur fossils in rock layers that formed well after the asteroid impact. These aren't just isolated bones that could have been weathered out of older rocks. They include well-preserved skeletal elements embedded in sediments that show clear chemical signatures of the post-impact world. Among the most significant discoveries is a hadrosaur femur found in association with pollen samples that tell a remarkable story. The pollen comes from plant species that evolved after the impact event, including early relatives of modern deciduous trees that emerged during the ecological recovery. This association suggests that the dinosaur lived during the early stages of ecosystem recovery, possibly 40,000 to 300,000 years after the asteroid strike. The preservation quality of these controversial fossils is itself telling. Unlike fossils that have been eroded from their original locations and redeposited, these specimens show excellent preservation with intact bone structure. The chemical composition of the bones matches that of the surrounding sediment, indicating they were buried and fossilized in place. Radiometric dating of the rock layers containing these fossils has yielded dates that consistently place them in the Paleocene epoch, the geological period immediately following the Cretaceous extinction. Multiple independent dating techniques have confirmed these ages. The rocks also contain the distinctive iridium layer that marks the asteroid impact, with the dinosaur fossils found in layers clearly above this marker horizon. The scientific debate surrounding these fossils has been intense. Skeptical researchers argue that the fossils represent reworked material, bones that were eroded from older deposits and subsequently reburied in younger sediments. Supporters of extended dinosaur survival point to several lines of evidence that argue against this hypothesis. The geographic distribution of these potential survivors is also significant. The fossil sites are located in what would have been relatively isolated and environmentally protected areas during the early Paleocene, river valleys and lowland basins that might have provided refugia where small dinosaur populations could persist even as global ecosystems collapsed. If some dinosaur populations did survive the initial catastrophe, their ultimate extinction would represent what biologists call dead clade walking, species that survive an extinction event but lack the genetic diversity or ecological support necessary for long-term survival. The potential survival timeline suggested by the fossil evidence presents an intriguing pattern. The latest dinosaur fossils appear to cluster in the first few 100,000 years after the impact, with no confirmed specimens from later periods. This suggests that while some populations may have initially survived, they were unable to establish stable, self-sustaining communities in the recovering ecosystems. The controversy remains unresolved, with new fossil discoveries and analytical techniques continuing to add evidence to both sides of the debate. What's clear is that the extinction of the dinosaurs was far more complex than originally imagined, a gradual process that may have unfolded over hundreds of thousands of years rather than the sudden event portrayed in popular culture. As the first year following the asteroid impact drew to a close, Earth remained a planet transformed, its skies still hazy with atmospheric debris, its landscapes scarred by the greatest catastrophe in 65 million years. Yet beneath the surface of this seemingly dead world, the patient work of recovery had already begun. The atmospheric recovery was the first glimmer of hope in an otherwise bleak world. The fine particles that had blocked sunlight for months were finally beginning to settle out of the atmosphere, allowing gradually increasing amounts of solar radiation to reach Earth's surface. The sulfuric acid aerosols that had created such devastating acidic rain were being washed out by precipitation. This incremental atmospheric clearing had immediate consequences for the few surviving plant communities. Hardy species that had maintained dormant root systems underground began to send up tentative shoots, testing the slowly improving conditions. These pioneer plants were often species that had previously been considered weeds, tough, adaptable species that could tolerate poor soil and variable water conditions. Ferns were among the first plants to stage a dramatic comeback, their spores having survived the catastrophe in soil banks and underground refugia. The phenomenon was so pronounced that paleobotanists recognize a distinct fern spike in the fossil record, a period when fern spores dominate pollen samples from around the world. The soil ecosystem, devastated by months of acidic rain and contamination, began its own slow recovery. Bacterial and fungal communities that had retreated to deeper soil layers gradually recolonized the surface, beginning the crucial work of decomposing organic matter and cycling nutrients. Marine recovery followed a different timeline, with some of the most dramatic changes occurring in the deep ocean, where conditions had remained most stable. Deep-sea communities of bacteria and small invertebrates had survived the surface catastrophe largely intact, and they now began to recolonize the devastated shallower waters. Plankton communities began to rebuild from the few surviving species that had endured the acidification and darkness. These populations initially consisted of only the most stress-tolerant species, creating marine ecosystems far simpler than those that had existed before the impact. Small mammals, the ultimate beneficiaries of the extinction event, began their remarkable evolutionary radiation during this recovery period. With large dinosaurs no longer competing for resources or posing predation threats, mammalian species rapidly diversified into ecological niches that had been closed to them for over 160 million years. Early birds similarly underwent rapid diversification, with different lineages exploring aerial niches that had been vacated by pterosaurs. Some developed specialized feeding strategies, others became seed dispersers for the recovering plant communities, and still others evolved into the first post-impact predatory birds. The recovery process revealed the critical importance of ecological interactions in ecosystem rebuilding. As plant communities re-established themselves, they created habitat and food sources for herbivorous animals. These herbivores, in turn, provided food for carnivores and served as agents of seed dispersal and pollination. By the end of the first decade after impact, recognizable ecosystems were beginning to emerge, though they bore little resemblance to their Cretaceous predecessors. These early Paleocene communities were characterized by low diversity, simple food webs, and dominance by opportunistic species. The century following the impact saw the establishment of more complex ecological relationships. Predator-prey dynamics became more sophisticated as both hunters and hunted diversified. Plant-animal interactions became more specialized as both groups evolved to take advantage of new opportunities. Mammalian evolution during this period was particularly dramatic. What had been a group of small, mostly nocturnal species rapidly diversified into forms adapted for every conceivable lifestyle. Some remained small and specialized, while others grew to sizes that would have been impossible in a world dominated by large dinosaurs. The millennium following the impact saw biodiversity beginning to approach pre-extinction levels, though the composition of life was fundamentally different. Mammals had replaced dinosaurs as the dominant large terrestrial vertebrates. Flowering plants had expanded their ecological dominance. Birds had diversified into forms that exploited every aerial niche. Climate recovery was a gradual process that continued for millions of years. While atmospheric clearing allowed temperatures to begin rising within the first few years, it took much longer for the complex climate systems that had characterized the Cretaceous to re-establish themselves. Perhaps most remarkably, the recovery process created evolutionary opportunities that would never have existed in a world still dominated by large dinosaurs. The mammals and birds that inherited the post-impact world were able to explore evolutionary possibilities that had been foreclosed for over 160 million years. The recovery from the asteroid impact stands as one of evolution's greatest success stories, a testament to life's incredible resilience and adaptability. From the ashes of the Mesozoic world emerged new forms of life that would prove even more diverse and successful than their predecessors. After decades of research, the true timeline of dinosaur extinction has emerged as far more complex than the popular image of instant catastrophe would suggest. The evidence paints a picture not of sudden death, but of a gradual decline that unfolded across multiple timescales, from the immediate hours of impact violence to the prolonged suffering that may have extended across centuries. The immediate aftermath was indeed catastrophic for most large dinosaurs. Within the first 24 to 48 hours, massive numbers of dinosaurs across North America likely perished from the thermal pulse, glass spheruleal bombardment, and initial atmospheric disruption. The evidence from sites like Tanis suggests that many animals died within hours of the impact. Yet this immediate die-off represented only the first wave of extinction. The fossil record reveals a more nuanced pattern, one that suggests different species and different geographic regions experienced extinction at markedly different rates. The largest herbivores, such as sauropods, likely disappeared within weeks or months as their enormous food requirements became impossible to meet. Medium-sized herbivores like ceratopsians and hadrosaurs appear to have lasted longer, possibly surviving the first year or even several years in some refugia. Their more efficient digestive systems and ability to process lower-quality plant material may have allowed them to survive on the dead vegetation that persisted through the impact winter. Carnivorous dinosaurs followed their own unique extinction timeline. Initially, the massive die-offs provided abundant carrion that may have allowed some predator species to thrive temporarily. However, this advantage was short-lived. Within months, the supply of fresh carcasses was exhausted. The geographic pattern of extinction reveals important insights into how environmental refugia influence survival. Areas with stable water sources, protection from acidic rain, and access to underground food resources may have supported dinosaur populations for extended periods. Body size emerged as perhaps the most important factor determining extinction timeline. The fossil record shows a clear pattern. Animals weighing more than about 55 pounds faced extinction rates, approaching 100%, while smaller animals had dramatically better survival prospects. The extinction process itself varied dramatically between species based on their ecological characteristics. Specialists faced faster extinction than generalists who could switch between food sources. Animals with rapid reproduction cycles had better chances of maintaining populations through genetic bottlenecks. The genetic consequences of population bottlenecks created their own timeline of extinction. Even species that initially survived the environmental crisis faced long-term extinction risk from reduced genetic diversity. Modern ecological theory suggests that the true end of the dinosaur extinction event might be measured not by the death of the last individual, but by the collapse of dinosaur-dominated ecosystems. From this perspective, the extinction was complete when dinosaur communities could no longer maintain their ecological functions. The implications of this extended timeline are profound for our understanding of both ancient and modern extinctions. Rather than sudden catastrophic events, mass extinctions may be better understood as extended periods of ecological crisis where species face prolonged struggles for survival. The story of the asteroid impact and the gradual extinction of the dinosaurs offers profound insights that echo across the vast expanses of geological time to reach us in our modern world. These lessons speak to fundamental truths about environmental change, the resilience of life, and the delicate balance that maintains the complex web of existence on our planet. Perhaps the most sobering lesson is how quickly stable systems can collapse when pushed beyond their limits. The Cretaceous world had been relatively stable for millions of years, a thriving biosphere where complex ecosystems had time to develop intricate relationships. Yet this stability was shattered in a matter of hours when environmental conditions changed faster than life could adapt. The factors that determined survival during the extinction event offer crucial insights for understanding resilience in the face of environmental crisis. Size mattered. Smaller organisms with lower energy requirements proved more adaptable than giants that needed vast resources to survive. Dietary flexibility was crucial. Generalists who could switch between food sources outlasted specialists adapted to specific resources. These survival characteristics have direct parallels in modern conservation biology. Today's endangered species often share traits with extinct dinosaurs: large body size, specialized diets, complex habitat requirements, and slow reproduction rates. Understanding why these characteristics made species vulnerable 66 million years ago can inform current efforts to protect biodiversity. The recovery process reveals life's remarkable capacity for innovation and renewal. While the immediate aftermath of the extinction was devastating, it also created evolutionary opportunities that had been impossible in a dinosaur-dominated world. This pattern, destruction creating opportunities for innovation, is a recurring theme in evolutionary history. The timeline of recovery teaches us about the patience required for ecological healing. While some aspects of environmental recovery occurred relatively quickly, atmospheric clearing within years, basic ecosystem function within decades, the restoration of full biodiversity took millions of years. The role of chance in determining survival highlights the unpredictable nature of extinction events. Many factors that determined life or death during the asteroid impact were essentially random. This randomness reminds us that conservation cannot rely solely on protecting the best species or habitats. Preserving diversity itself provides insurance against unpredictable future challenges. The interconnected nature of ecosystems, revealed by the cascading extinctions that followed the initial impact, demonstrates how the loss of seemingly unimportant species can trigger broader ecological collapse. Modern ecosystem management must consider these complex interactions rather than focusing on individual species in isolation. The extended timeline of dinosaur extinction challenges simple narratives about environmental catastrophe. Rather than sudden dramatic events, Mass extinctions often unfold as prolonged periods of stress, where species face gradual decline, punctuated by periodic crises. Perhaps most importantly, the dinosaur extinction reveals the deep interconnectedness of Earth's systems, atmosphere, oceans, climate, geology, and life itself. The asteroid impact affected all these systems simultaneously, creating cascading changes that reverberated through the entire Earth system for millions of years. Finally, the dinosaur extinction demonstrates both the fragility and resilience of life on Earth. While individual species and ecosystems proved vulnerable to rapid environmental change, life as a whole showed remarkable persistence and creativity in the face of seemingly impossible challenges. These lessons from deep time offer both warnings and hope as humanity grapples with its own environmental challenges. They remind us that change is constant in Earth's history, that stability is temporary, and that adaptation and innovation are life's responses to crisis. As we reach the end of our journey through that catastrophic spring day 66 million years ago, let us return once more to that peaceful forest clearing where we began. Picture again that massive Triceratops, grazing contentedly in the morning light, unaware that the flash in the southern sky would change everything. In that moment, neither the dinosaur nor any other creature on Earth could have comprehended the magnitude of what was beginning to unfold. But now we understand the full scope of that story, not the simple tale of instant extinction that we might have imagined, but rather a complex narrative of struggle, adaptation, and ultimately transformation. The Triceratops in our forest clearing may have died within hours of the impact, or perhaps it survived for weeks, months, or even years as part of one of those controversial populations that may have persisted in isolated refugia. We may never know the fate of that particular individual, but we do know that its kind eventually yielded their ancient dominion over the Earth. Yet this ending was also a beginning. The death of the giant reptiles that had ruled for over 160 million years created space for other forms of life to flourish and diversify. In the canopy above our Triceratops, small feathered creatures, the dinosaurs that survived, would eventually give rise to the incredible diversity of birds that grace our modern skies. In the undergrowth beneath its feet, tiny mammals would emerge from their shadowy existence to inherit a world of possibilities that had been unimaginable during the Age of Giants. The asteroid that ended one chapter of Earth's story simultaneously began another. The mammals that today walk, swim, climb, and fly across our planet, including our own species, owe their evolutionary opportunities to that catastrophic spring morning when a mountain of rock and ice fell from the stars. We are, in a very real sense, the children of that ancient catastrophe, our existence made possible by the same forces that brought an end to the dinosaurs. This perspective offers a profound lesson about the nature of change and renewal in the natural world. What appears to be an ending is often also a beginning, destruction creating the conditions for new forms of creation. The cycles of extinction and radiation that characterize Earth's history demonstrate that life is not diminished by catastrophe, but rather transformed by it. As you drift towards sleep tonight, perhaps you can imagine the deep rhythms of geological time, the slow dance of continents, the patient work of evolution, the endless creativity of life in all its forms. That Triceratops, grazing peacefully in its Cretaceous meadow, was part of a story that stretches from the very origins of life to this present moment, and onward into futures we can barely imagine. The same stars that witnessed the fall of the dinosaurs shine down on us tonight, their light carrying messages across the vast distances of space and time. In that light, the 66 million years that separate us from the age of dinosaurs becomes just a brief moment in the cosmic story of which we are all part. The dinosaurs had their time in the sun, as mammals are having theirs, as other forms of life will have theirs in the countless ages yet to come. Rest now in the knowledge that you are part of this continuing story, a story that includes both the catastrophic end of ancient worlds and the quiet beginning of new ones. Like the tiny mammals that survived that long-ago catastrophe by being small, adaptable, and patient, life continues to find ways to persist and flourish, despite the challenges it faces. Tomorrow will bring its own light, as it has for billions of years, illuminating a world that bears the quiet signatures of that ancient catastrophe in its rocks, its fossils, and its living communities. But tonight, let the deep peace of geological time wash over you like a gentle tide, carrying you into dreams of ancient worlds and the endless resilience of life itself. The age of dinosaurs may have ended on that spring morning long ago, But the story of life continues with each breath you take, each heartbeat that connects you to the unbroken chain of existence that stretches back to the very beginnings of our planet. In that continuity, there is both wonder and profound peace. Sleep well, knowing that you are part of the greatest story ever told, the story of life on Earth, with all its catastrophes and recoveries, all its endings and beginnings, all its ancient mysteries and endless possibilities for renewal. The stars continue their patient watch overhead, just as they did when the last dinosaurs walked the Earth. Time itself moves like a gentle river, carrying all things toward rest and renewal. Seeds sleep deep in the soil, waiting for their season to come again. Somewhere in the vast darkness, new worlds are being born. And in this moment, as your breathing slows and deepens, you become part of that same eternal rhythm, the rise and fall of life, the gentle persistence of existence, the quiet promise that tomorrow's dawn will bring new possibilities to a world that never stops creating itself anew. Let the soft whisper of wind through ancient forests carry you now into the deepest rest, where time dissolves into timelessness, and all the stories of the world become one story, the story of life itself, forever beginning, forever becoming, forever finding new ways to bloom in the endless garden of existence. If you've enjoyed this video, then like it and subscribe to our channel to stay updated on new uploads. Sweet dreams, my friends.